we have been looking at how to solve or how to get the general solution for a linear homogeneous system of differential equations like this, with constant coefficients. And we have seen that it all comes down to solving the eigenvalue problem for A. That is the way to decouple what is initially a coupled system of differential equations. And the way that actually works is if you have an eigenvalue-eigenvector pair, like V an eigenvector and lambda an eigenvalue, then using these two ingredients, you can build a solution like this, a solution to the differential equation. E to the eigenvalue times time times eigenvector. And here, all the time dependence is in this scalar in front, and then the eigenvector just has some constants in it. So, does this always work? Well, the goal to get a general solution, the goal is to get two linearly independent solutions, or n linearly independent solutions, if it's an n by n system. Say 2 by 2, then you need two linearly independent solutions. Will you always get that? Well, you always get at least one eigenvector and eigenvalue pair. You're not guaranteed a second one. So, where that comes from is, so the guarantee that there is at least one comes from the fact that lambda's being an eigenvalue is a polynomial condition. So for lambda to be an eigenvalue, it has to be a root of the so-called characteristic polynomial of A. So this polynomial, determinant A minus lambda identity. So this equation, this polynomial equation, has to be true in order for lambda to be an eigenvalue. And we know that every polynomial has at least one root. Every polynomial equation you write down like this, of degree greater than 0, every polynomial equation, say of degree 2, every quadratic polynomial, for example, has at least one root, as long as you allow for complex roots. So if you allow for complex roots, there's no trouble getting at least one eigenvector-eigenvalue pair. Sometimes there's trouble getting a second one, and sometimes not. So today I want to look at one of those situations where things are good. You actually do have no trouble getting a second one, but you do have to use complex numbers. So a situation where this quadratic polynomial has complex roots. So in this situation, when you have complex eigenvalues, when you have complex roots to a quadratic polynomial, they always take the form of a complex conjugate pair, right? Like alpha plus I beta, alpha minus I beta. So let's say lambda is alpha plus I beta. Let's call this one lambda 1, and then lambda 2 is alpha minus I beta. Since you do actually have different eigenvalues, you're guaranteed by some linear algebra theory that you will get linearly independent eigenvectors. The only dangerous situation where you might not get linearly independent eigenvectors is the situation where you have repeated eigenvalues. So this is not that. This is still pretty good, even though you're seeing complex numbers. This is good. Now, if you remember, when we were dealing with second-order systems of differential equations from Chapter 2, in the complex eigenvalue or complex root case that we had there, we only really needed to care about one of the two roots, because the other one didn't provide any more information. So what about here? If I know one root, will I automatically know the... Well, of course, if I know one root, then I automatically know the other. The other is the complex conjugate. So I didn't need to call this lambda 1, lambda 2. Maybe a better naming system would be lambda and lambda bar, right? The bar stands for complex conjugation, which is flipping the imaginary part, flipping the sign on the imaginary part. So yeah, if I know one root, then I automatically know the other when the root is complex. But what about eigenvectors? So let's say this is the eigenvector that goes with lambda. Let's say it's w plus iz, then will I also automatically know the eigenvector that goes with the other eigenvalue, lambda conjugate? It turns out it is actually, the other eigenvector is actually this. Let's call it v bar, because it is worthy of being called v bar. It's what you get by flipping the sign on the imaginary part of this vector. So by the way, when I write a vector like this, I'm just treating I as a complex scalar in front. And I'm thinking of w and z as like the real and imaginary parts of this vector. So it's, let me give you an example, since I think I'm writing this for the first time, this kind of notation. Let's say v is like 1 plus 2i, 3 plus 4i. Then you can write that as a real vector, 1, 3, plus i times an imaginary vector, 2, 4. So what I mean when I write it out like this is that w would be 1, 3, and z would be 2, 4. So these individual vectors, w and z, would be vectors with real entries. And then I've sort of portioned off the parts that have an I multiplied by them and the parts that don't. So anyway, I think it's fun to try to see why this actually works. Why is it that when you know one eigenvalue, eigenvector, then you flip, and then you take the conjugate of the eigenvalue, why does taking the conjugate of the eigenvector actually work? Well, here's a simple way to put it, I think. Use the fact that complex conjugation, this operation that I'm denoting by putting an over bar, complex conjugation distributes over addition and multiplication of complex numbers. So let's say you have this being true, AV equals lambda V. That's what it means to say lambda and V are an eigenvector eigenvalue pair. So let's say we have this being true. Now conjugate both sides. So then this is true, right? You can always do the same thing to both sides of an equation. Now focus on the right side. That's simpler. That's just a bunch of components, two components in the 2 by 2 case. Each looks like a multiplication. Lambda times the first component of V, and then the second component is lambda times the second component of V. And each of those is getting conjugated. Well, like I just said, conjugation distributes over these algebraic operations. So conjugate of a product is the product of the conjugates. So when you apply that to each component, it lets you do this. View it as lambda bar times V bar, where by V bar I mean this thing here. This one is a little bit more complicated, but if you think about the two components here, they're just going to be sums of products of numbers, right? So how to put this, the first component and the second component will each be some entry from the matrix A times an entry from the vector V, plus another entry from the matrix A times an entry from the vector V, and so on and so on. So they're all just these products. And when you apply conjugation to them, the conjugation distributes over the sum and then over the products. What it comes down to is that we can do this. So this is just the algebra of conjugation that's powering this. And finally, A is actually a real matrix, right? It has 0 for its imaginary part. So what happens when you conjugate something that has 0 for its imaginary part? Nothing happens. You just get the original thing back. And so look what we've arrived at. What's written here now is exactly the statement that lambda bar is an eigenvalue for the original A with eigenvector V bar. And this qualifies as giving us an eigenvalue eigenvector pair as long as V bar is not 0, which it's not. V bar is not 0 if V was not 0, right? Eigenvectors should not be 0. So yeah, we get another eigenvector eigenvalue pair for free. And you will see me use this to save some work later on if I do need to get the other eigenvector when I have one complex one, then I'm just going to take the complex conjugate. So anyway, you can, like we have been doing with the real case, you can use this procedure to construct a solution, but it will be a complex valued solution. We've been here before. We've had this issue where we had a differential equation, x prime equals ax. We wanted real solutions, but we found a complex solution using our technique instead. Nothing wrong with this. So let me just write down what it is. It would be x of t equals e to the eigenvalue t times eigenvector. And now let me write out the eigenvector in terms of real and imaginary parts. So scalar times vector, and they have complex entries. So what did we do last time, back in chapter 2, when we had complex solutions and we wanted real ones? Well, we made sort of a general argument that anytime you have a linear homogeneous differential equation, so something like this, L of unknown function equals 0, where L is a linear operator with some derivatives in it. Anytime you have this, then if you have a solution, a complex solution, the real and imaginary parts must also be solutions. So this is what we showed back in chapter 2. Well, what's changed now? Now it's a vector of functions rather than just one unknown function. It's a list of unknown functions. But the linear algebra is the same. The argument we made before works the same. You just have to put these little vector symbols above things. So it is still true that, let me write this out. Basically, this principle that I just wrote is still true here. For a linear homogeneous differential equation with constant coefficients, the real and imaginary parts of any given solution are going to also be solutions. And I may have forgotten to say originally that we're talking about a differential equation that starts with real coefficients. So that would be the situation where you're interested in a real solution. So A, we're assuming A is starting out as a matrix with real coefficients, with real entries. If the entries of A are not real, then this polynomial is a polynomial with possibly complex coefficients in it, which is fine. It still has a root, but all of this discussion goes away. You no longer have roots coming in pairs like this with complex conjugation working. You would no longer have A bar equals A. So all of this nice stuff with things coming in complex conjugate pairs, this requires that your original differential equation has constant coefficients. Okay, so what are we going to do? Once we get a solution like this, take the real and imaginary parts. And that's going to give us two real solutions. And it will actually give us two real linearly independent solutions. So in fact, that's enough. That's all we need. This cannot even give us any more. So we can just throw the other pair away. Or if you want, use this pair and then throw this one away, whatever. So you only need one of these eigenvector eigenvalue pairs. You'll get two linearly independent solutions. So what are they? We can actually, writing things out like this, we can just provide the general form of what they will look like. So if, say, you have a complex eigenvalue, complex eigenvector that goes with it, you write out your eigenvector as a real vector plus I times another real vector, then construct your complex solution. This will be a complex solution. Then see if you can make it clear what are the real and imaginary parts. So we have a scaling going on here, which means in each of the components of this vector here, in each of the components you have a multiplication. Now, the real and imaginary parts of a product of complex numbers is kind of complicated, and we're definitely not going to get anywhere without knowing the real and imaginary parts of this exponential part. But we know how to do this one. It's e to the alpha t. Actually, let me pull out an overall factor of e to the alpha t times e to the I beta t. What's e to the I beta t? It's cosine beta t plus I sine beta t. All right, now we're getting somewhere. That's now showing what is its real and imaginary part. And then we still have this vector here. But I'm still not seeing clearly what are the real and imaginary parts of the overall expression. But now to see what they are, it remains to multiply. So let me keep this e to the alpha t sitting in front. That does not bother me because it's overall real. It's just an overall real factor on top of everything. And then here, let's see, I have cosine beta t times w. So when I say times, I mean scaling. So this is a scalar and that's a vector. Cosine beta t scale w. And then, let's see, I have another real looking part, which is when I multiply this, by which I mean scaling again, so this scalar times this vector, then I get an I squared, which is -1. So I have minus, get rid of these lines, minus sine beta t z. And then, I think I'll need more room here. Then there are also cross terms, and those will have i's on them, the cross terms. So one cross term is cosine beta t scaling z, and then there's an I in front. And the other cross term is sine beta t scaling w. All right, and then now I can see what are the real and imaginary parts of this. So x real, let's call it, of t, the real part of x of t, is e to the alpha beta times this stuff. E to the alpha t times this stuff. Like that. And let's say x imaginary is going to be e to the alpha t times, well, times this stuff, but I'm not picking up the I, right? The imaginary part is this stuff. It's supposed to be real. This is real. It's just the stuff that has a factor of I on it in the original thing. Okay, and I guess these are actually pretty bad names here, x real, x imaginary, because I don't care that one started its life out as a real part and the other started its life out as the imaginary part. I don't want to know their origin stories. I just want to know that these are two linearly independent solutions to the original differential equation. That's all I need to know about them. So x1 and x2, and now we can write our general solution. So there's nothing complex going on here anymore, right? Everything you see here is real. W and z, these are real vectors. They're the real and imaginary parts of v. They are real vectors. So now we can finally write the general solution. Is c1 this plus c2 that. And we can do our usual thing. Given initial conditions, we can try to solve and get c1 and c2 to satisfy the initial conditions. So this is victory. This is the best possible situation you can have, always, when you have two linearly independent solutions like this. Sorry, actually you always have two linearly independent solutions. That part doesn't ever go wrong. The part that can go wrong is two linearly independent eigenvectors. That's not always available. So we have that here, and that's the best possible situation. It really makes things easy. You have these extra calculation steps when the eigenvalues are complex, but it's really just, more writing. It's not really more complicated algebraically. We're also starting to get a hint as to what the real and imaginary parts do to these solutions. So, of the eigenvalue. So you get your complex eigenvalue, alpha plus I beta. You can see alpha plays the role of an exponential growth or decay rate in front of any solution, actually. So x1 and x2 both have a factor of e to the alpha t on them. So if alpha is positive, then all of our solutions have this exponentially growing scale factor in front. That's if alpha is positive, if the real part of your eigenvalue is positive. If the real part of your eigenvalue is negative, then you have exponential decay out in front. So you can tell a lot just from looking at alpha. And then what if alpha is 0? If alpha is 0, then this part isn't even there, and you'll get something, something else going on. Pure oscillation. Okay, so we will look at that in a little bit more detail. And beta, so where does beta show up? Only inside the trig functions here, sine and cosine. That's where beta shows up. It's playing the role of an angular frequency, right? So it's kind of like a frequency of oscillation. But to understand the kind of oscillation that's going on, we will have to draw some phase diagrams and look at the trajectories that we see to see like what exactly is meant by oscillation.